Hi, and welcome back to Understanding Motors. Last episode, we proved that we can eliminate torque ripple while simultaneously minimizing the current in the D direction by having our three-phase currents be sinusoidal functions of our rotor angle. However, there are multiple ways of achieving this, and it isn't immediately obvious which method is best. By the end of this episode, however, we're going to have arrived at the industry standard method of optimized commutation. So, let's get into it. So we're going to start today by talking about feedback control. For some viewers, feedback control may be a super familiar idea, and for others, it may be entirely foreign. If you're in the latter category, don't worry, we're not going to take a deep dive into control theory here, but I think it's a useful framework through which we can understand achieving our desired current. In a lot of applications, such as, say, fans or older washing machines, motors are run in what is called an open loop fashion. What this means is that the magnitude of the voltage applied across the leads of the motor is not necessarily a function of the current running through the motor at that time. You can kind of think of this as having the voltage pattern being pre-scheduled. However, in cases where you care about the motor's angular position, or if you want to dictate the velocity of the motor system and there are external forces being applied, you would want to control it via what's called closed-loop control. I find that this is easiest to explain via an example. So, say that you want to control the angle of your motor. You would come up with a position reference signal, which you would then pass to your controller. The controller would look at the error between the current orientation of the rotor and the position you specified you wanted. It would then command a torque to the motor to turn it to the desired position. As we talked about in episode 2, torque is proportional to current, so really, the controller is commanding a current to the motor. However, we don't have a way of just dictating an exact amount of current running through the motor. Instead, we have to make a second, nested controller here, which looks at the current we want running through our motor as dictated by the first controller. It then compares it to the current we have running through our motor and modulates the voltage being applied to our motor phases based on the error between the actual current and the desired current. Cool, so that's a super basic overview of what closed-loop current control is. However, this nested current controller has one issue that is fundamentally different than the position controller. Unlike rotor position, which is a one-dimensional number, both current and voltage are two-dimensional. You can think of these dimensions in a rectangular Cartesian plane, as we did with the alpha-beta axes. However, I find that for this conversation, the most useful way to think of these is in a polar reference frame, meaning that we're describing the vectors in terms of a rotation angle and a magnitude. The reason I think this is useful is that while the magnitude of the current commanded and the voltage applied are functions of the error terms going into the controllers, the angle at which they're applied is a function of the orientation of the DQ axis, and thus the rotor's position. So I like to kind of think of these two variables as being separately controlled. The magnitudes of the vectors will be determined by the feedback control loop. Meanwhile, the angle of application will be a function of rotor angle and will be handled by the chosen method of commutation and pulse width modulation to the H-bridge. We're going to talk more about designing the closed-loop controller, which will dictate the magnitude of these signals in a later episode when we get a bit more into the systems analysis of motors. But right now, we're going to talk a bit more about commutation and the different ways you can modulate your voltage. One of the simpler ways we can modulate our voltage has already been discussed here. In fact, it was the primary focus of episode 6, 6-block commutation. Here, by using the signals from the Hall effect sensors as a low-resolution angular measurement, we dictated the angle of application of our voltage vector, and thus of the current flowing, as a super discrete function of our rotor angle. So, if you were using 6-block commutation with your feedback controller, your current controller would look at the current running through your motor, it would then compare it to the reference you provide it, and generate the magnitude of a voltage signal to be applied. This voltage signal would then be divided by the supply voltage of the system to find the duty cycle which you would want to apply to the MOSFETs of the H-bridge. If the commanded voltage was above your supply voltage, you would simply saturate the duty cycle at 100%. Finally, these duty cycles would be supplied to the appropriate FETs as dictated by your commutation scheme. where a positive 100% duty cycle corresponds to the high side MOSFET being active for 100% of the time, and a negative 100% duty cycle corresponds to the low side MOSFET being active 100% of the time. Note that this commutation pattern is for positive torques. If we wanted to produce a negative torque, we simply flip this commutation scheme about the x-axis. For all the reasons we've talked about in the last couple episodes, torque ripple, unwanted d-axis current, and such, 6-block commutation leaves a lot to be desired. However, if you have a more resolute method of angular sensing, like an encoder for example, you can improve your method of commutation. We know that the resistor-inductor circuit that is a motor acts as a relatively fast low-pass filter between voltage and current. So, at low to medium rotation rates, you can produce a sinusoidal current vector which rotates with the motor's angle by inputting voltage vectors which rotate at the same rate with the motor's angle. But how do you actually do that in the real world? Well, just like with block commutation, the output of your current control loop would specify a voltage magnitude to be applied. Again, you would then divide this by your supply voltage and saturate at 100%. Now, however, instead of applying this duty cycle full blast to whichever FET would be dictated by the block commutation, you would multiply this duty cycle by your A, B, and C sinusoids, which are functions of theta. This produces 3 duty cycles between negative 100 and positive 100%, which you can then output accordingly to your H-bridge. However, while this commutation scheme will allow for you to better control your current to the Q-axis, and by phase shifting your sinusoids forwards or backwards by some angular offset, you could modulate current in the D direction if you wanted to, say, field weaken, there is one nuanced downside to sinusoidal commutation. At no point during sinusoidal commutation are you taking full advantage of your voltage range. But what do I mean when I say this? Well, when we're applying, quote, a voltage, really what that means is applying a voltage differential. So the absolute magnitude of the voltage being applied to phase A doesn't really matter. What matters is the difference in magnitude of the voltage applied to A versus that to B and C. Kind of like how if you jumped from a platform that was 100 feet in the air onto another platform that was 99 feet in the air, gravity was only accelerating you for that 1 foot. But if we plot the sinusoidal functions of voltage being applied to phases A, B, and C, we notice that at no point are our phases spanning the full range of supply voltage possible. In fact, if we plot the voltage differential, so the highest voltage minus the lowest voltage for each angle on this plot, we see that the maximum differential we're using is only 86.6% of what our system could do. And this brings us to the industry standard way of modulating our voltage, space vector modulation. Just like with sinusoidal modulation, space vector modulation maintains a voltage differential which rotates with the motor angle to stay in line with the Q-axis. However, through some clever math, it takes full advantage of your supply voltage. I personally find that the easiest way to show how it works is just to demonstrate the transformations that take the voltage curve from the sinusoidal commutation waveforms and transform them into the space vector modulation voltage signals. Because we know that our voltage differential could theoretically be increased by 1 over 0.866 or 15.47%, we're going to start by multiplying our voltage signals by 1.1547. However, this obviously creates a new problem. While we would now be applying the maximum voltage differential our supply voltage could provide, we would also be required to command a duty cycle of 115%, which is by definition impossible. But here is where we get creative. To start with, I want to remind you again that it's not the absolute value of the voltage that matters, it's the voltage differential. So if we look at one of these places where we would need to command the voltage to high for 115% of the time, well, what's being applied on the other side of the circuit? Here we're only commanding the other two phases to ground at a 58% duty cycle. So accounting for the fact that the circuit dynamics will filter the PWM'd voltage into a pseudo-continuous voltage signal, the ability of the voltage differential to drive current would be the exact same for this location if, instead of having the impossible 115% duty cycle and 58% duty cycle, we shifted all 3 phases down by 28.8%, such that one was connected to high 86.6% of the time, and the other two were connected to low 86.6% of the time. In the same way, we see that the points when the low side would be required to connect to ground with 115% duty cycle, we could shift the common voltage of the three up by 28.8%, such that the three duty cycles were again 86.6%. So, in order to bring the negative 115% sections up and the positive 115% sections down, we will add a triangle wave with peaks at these locations to all three of our sinusoids. Now, using this modulation scheme, we're taking full advantage of the voltage range made available to us while keeping our required duty cycles at or below 100%. So, that's space vector modulation, which is generally regarded as one of the best ways to perform motor commutation. However, like we discussed in episode 7 with block commutation, there are still many different ways you can perform your actual PWM switching for any given commutation scheme. So next episode, we're going to look at the best way to perform space vector modulation in the real world.